Okay, this is a example for the first, what we call optimization question. Um, we've done the min-max, and the min-max, remember, how we find min and max of a function is we check the endpoints and we check the critical numbers. And that's going to be the same exact thing we do in the word problems. Now, the word problems are a bit simplistic, but the hope is that when you see the word problems, you can see why this is actually kind of an important thing. You can actually get a degree in basically this type of thing. It's one of the important parts of doing running a business. This was called the marginal cost of doing business. And when I talk marginal cost is a fancy word for the derivative of cost, right? The first derivative of cost is called the marginal cost. You may know that from AP economics. But anyway, so don't be worried about all the fancy words and stuff, optimization and marginal cost and all that. It's really the same stuff we've been doing, but we've been doing it with just regular functions. We want to do this with an actual equation, word problem. So let's make sure we understand the question that we're trying to answer, and then realize, oh, we know how to do that because we know how to find max and mins. Okay, but one thing about word problems is you're only going to be finding the max or the min. Like, you don't want to maximize your cost. You want to minimize your cost. You don't want to, make it expensive. You want to make it cheap. So we're going to do a couple of what we call marginal cost type questions. And again, they're going to be a little oversimplified, so just let that go, okay? But I think if you watch how this works, you'll go, oh, actually, in a more complicated situation, this would be kind of useful to know the calculus. Okay, so suppose you have a lighthouse. So there's on an island. So there's an island out here, and there's a straight shoreline here. Okay. Now, obviously, shorelines aren't straight, so just again, this is oversimplified, but kind of let that go. Okay, so down here is a house with electricity. And we want to bring electricity out to this newly constructed lighthouse. Now, the lighthouse, we're told, is 8 kilometers from the ocean, and that means perpendicular from the shoreline, and 10 kilometers down the beach. So the house is here, so you have to walk 10 kilometers down, then you'd have to swim 6 miles out if you wanted to get to the island. Now, suppose it costs 600 per kilometer to lay the wire down the beach. So to go on the beach, it costs $600 per kilometer. And crap, sorry, let's change this to 1,000. We want to make it more expensive to go underwater. Otherwise, we just go underwater. So let's say it costs 1,000. That's a poorly written 1,000 there. It might be hard to read on the video, but that's 1,000. 1,000 to go this way. So first thing you might think to yourself, well, it's cheaper to go underwater. Sorry, it's cheaper to go down the beach than to go underwater because it only costs 600 per kilometer down the beach, and then it costs 1,000 to go underwater. So one person might say, let's go down the beach and then go across. And so you go 10 kilometers down the beach at 600, and then you go 8 miles out at 1,000. So what's that? 6,000, 8,000. So what's that? $14,000. Now, if you want to make the question easier, which we're going to do in a little bit, we'll just use 6 and 10. Well, instead, we'll do it in terms of hundreds of dollars instead. But let's just keep all the zeros right now. So one way to do it is to run the wire down the beach because it's cheaper, and then minimize the amount of wire that goes out to the underwater because it's more expensive to do it underwater. Now another person might go, wait. On the other hand, it's more expensive, but boy, that's a long way. That's 18 miles or 18 kilometers of wire I need. Okay, even though it's more expensive to go underwater, it might be cheaper just to go all the way from point A to B underwater the whole way. Now, we use Pythagorean theorem. 10 squared plus 6 squared, take the square root. So this is 12.8. So, you know what? My blue's dying on me here. Let's see if I can try another blue. 12.80625 times 1,000. One other possibility is to go all the way out there And so what is that? 806 point. And it turns out that would be cheaper. So it'd be $14,000 to run it down the beach and then go out. And then it would be $12,806.25 to just go straight out. Now, and you probably know where I'm headed with this. We didn't check every other possibility, didn't we? We could just go partway down the beach and then head out. And this is where the calculus comes in. Remember, what I just checked was the endpoints. I can go straight out or I can go all the way down. But what about all the points in between? Well, that's when we need the calculus, okay? It turns out there's going to be a point partway down. In other words, what we're going to probably want to do, as a matter of fact, I know we're going to want to do because I've actually done the question before, is I'm going to go partway down and then come out. But what point, where is the what we call the optimal point to head out to the, how far down the beach do I go before I head out to the island to minimize this cost? In other words, I can actually do it for less than the $12,806.25. So what I need, and this is where it gets a little more complicated for students, is I need the cost equation. It's not that hard. Now, what I'm going to do, and we've done this in math a lot, more in Algebra 1 than we've done in this class, is if this is 10, I could break it up as into x, and then this piece would be 10 minus x. We've done that before in algebra. If you're going to break a whole number up into two pieces and you're going to call one piece x, the other piece is going to be the whole distance minus x. So x plus 10 minus x, obviously the x will cancel and you'll get 10. Now, you might go, Mr. Peters, how come you didn't call that x? Because it'll make the, trust me, the algebra goes a lot easier if you make this the x. Because I want to make my Pythagorean theorem here, I won't have to do, when I do a squared plus b squared to get this distance out underneath the water, I won't have to do 10 minus x squared. So trust me that when you break it up here. So instead of finding this x, I'm going to call the distance from here x. You could do it the other way, it just makes it more complicated. Okay, so now, how far down the beach do I go? 10 minus x, and that costs 600. Then, at some point here, I'm going to cut out. Now, what is that? Now, this gets a little more complicated here, and this is kind of why you want to make sure that you 8 squared plus x squared. Take the square root. So that distance there, now that costs 1,000. Okay? And now I'm going to write it as a fractional exponent, so I can take the derivative easier. 8 squared is 64 plus x squared to the 1/2. Now, this is where you have to realize that we're going to do the same thing we've been doing in our homework. Slightly more complicated equation here, though. Let's do two things to make life easier. Well, no, let's just do one thing. Let's just distribute the 6 in 600 minus 600x plus 1,064 plus. I'm just going to distribute that in. So when I go take the derivative, hopefully it'll be easier. Okay, so now what you want to think about is what we did is we have our equation. Now remember what we have to do. Now pretend this is like the homework we've been doing for the last couple of weeks. C is like f of x, and here's my equation, okay? What do I want to do is I want to check the endpoints and the critical numbers. Now I'm heading somewhere with this, so just bear with me. This is more philosophical than practical. Because the answer, you guys, I promised you that on any homework question or test question, the answer to the question will be when the derivative equals 0, which is not going to be the endpoints. Is when x is 0 or 10, right? If x is 0, then that means this whole distance is 10, and that's 8. So if I put 0 in, I get 10 minus 6 plus, if I put 0 in, 64, square root of 64 is 8,000. You might go, oh, Mr. Peters, that's just this number here. Yeah, that's that. Remember, what I actually already checked the endpoints, but I'm just doing it again to kind of make you, this is more to philosophically bring it home that, oh, this question is really just the same as the last question. What if I go straight out? That's when I would make x 10. What if x is 10? then, oh, that would be 0. 10 minus 10 is 0. And then I get here, 10 squared is 100, so I get a square root of 164, so I get 1,000 times the square root of 164. And then, again, we worked that out. That was 12.8 times 1,000. And so we've already checked our endpoints already. Now, remember, when we actually do the homework, don't worry, it's not going to be the endpoints. I'm going to make sure that the cheapest way to do it is somewhere between the endpoints, because it's not all that interesting if it happens at an endpoint. Okay, so remember the other thing, so we did our endpoints, now we need what's called the critical numbers. And that is when that derivative of c is equal to 0, okay? Remember, the critical number is when the derivative of c equals 0. Okay, so what am I going to do? Okay, so I need the derivative. So the derivative of 6,000 is 0. The derivative of negative 600 is negative 600x. Now, be careful here with this derivative, is because it's been a while since we've done a chain rule. You bring the half down, say my 1,000, a half, 64 plus x squared to the negative 1/2. Remember, we have to do a chain rule with what's inside. So there's the derivative. Now, we have to figure out when this thing equals 0. Okay, so what do I get? 0 equals negative 600 plus the half and the 2 cancel, and so I get 1,000 x all over the square root. Remember what half power means. So I've got to solve that equation. Now, I'm going to give you a big, huge piece of advice right now. Huge piece of advice. Reduce this. Divide both sides by 100. And then actually divide by 2. So you don't have to do this step, but boy, if you trust me on this, it'll make the math a billion times easier. What happens is if you don't do it, you're going to be getting really huge numbers, because what we're going to do is eventually we're going to square both sides. Oh crap, they're supposed to be 5x. There we go. Okay, so move the 6 over to the 3 over to the other side. Square root of 64 plus x squared. Now the trick here is to square both sides. 9 equals 25x squared divided by 64 plus x squared. Now I'm running out of room, so I'm going to come over here. Cross multiply this over to this side. Now don't multiply the 9 times the 64. If you have a calculator, you can do it, but you're wasting your time. Just leave it as 9 times 64 plus 9x squared. So do the denominator over, equals 25x squared. 9, you'll see why in a second. 16x squared. 16 goes into 64 4 times. Now I can multiply, and I get x is 6. So there's the critical number 6. So notice that it's the same thing we've been doing, except it's a word problem. So now what does 6 that mean? If that means this is 6, so if this is 6, 10 minus 6 is 4. Now this may be faster for some than others. If that's 6 and that's 8, this is 10. Because this is 3 times 2, 4 times 2, 5 times 2. Or you could do, if you need to, you could do a squared plus b squared. 6 squared is 36 and 64. 64 and 36 adds up to 100. The square root of 100 is 10. So what does that mean? I have to go 4 down the beach and then 10 out to the thing. So if I go 4 down the beach, 4 times 600 is 2,400, and then 10 out. 10 times is 1,000. It's 10,000. Now it's not a lot less, but notice that number is actually smaller than the other two numbers. 12,400. It's about $400, $406.25 less than that. So if we could actually save $400, a little more than $400, if we go down 4 kilometers before we head out to the island. Now again, there's a couple things to keep in mind. The reason this is such a big deal is what if this wasn't a $12,000 project? What if it was a $12 million project? Well, if you could save $500,000 by knowing exactly where to head out. Like I said, this has a lot of applications. Like if you have a conveyor belt with building cars, where do you put the parts so that the people have to walk the minimum amount? You'll see downtown LA, they have signs that will say they're trying to have maximize traffic flow. You can get there are jobs that really your whole job is to try to optimize. What is the optimal thing to do? Now, this is an oversimplification, obviously. So, what you're going to do is you're going to go down the beach 4 kilometers and then head out to the house. Now, why is that the only point we have to check? Because remember, max and min only occur at critical numbers. That's why we had to take the derivative instead of equal to 0 and solve this equation. The only point, I don't have to check every frickin' step down the beach and see which one's the cheapest. It's either at the endpoints or it's at the critical number 6. So it either has to go all the way down the beach, straight out, or in this case, we want to go down where x is 6. Now remember, I called that x. That means we just go 4 kilometers down the beach. Hopefully this will make you see that there's actually, it's kind of an important skill to be able to what we call optimize. And optimization is a fancy word for when I'm trying to optimize the cost. Is remember, this a fancy word for this is called the derivative of cost is called the marginal cost. So you want to figure out the marginal cost and set that equal to 0, solve that equation, and then you find the ideal number of things to make to minimize the cost of production or whatever you're trying to minimize. Okay.